Okay, and just confirm I'm audible and slides are visible. Please confirm.
So the slides are not visible. You are audible perfectly.
Slides are not visible, no? Are they visible now?
No, sir.
Wait, then let me stop.
Now it's visible, sir. Now it's
visible.
visible.
Good.
Yes, sir.
Simplifying switching functions, that is visible.
Yes, sir.
Yes, sir.
Oh, good. Thank you. Okay. Now let's move to the next topic. Is that what we saw, that what is the definition of an Boolean algebra and what are some of the postulates of Boolean algebra, some of the axioms of Boolean algebra, and how these axioms help us is that they help to convert one expression to another equivalent form. Equivalent in the sense that for all input, both expressions would evaluate to the same value, either 1 or 0, they would evaluate to the same value. And so why, if they're equivalent, why you are doing these transformations? And by the way, we are doing these transformations by some rule of equivalences, which are basically the axioms of the Boolean algebra, which says that this expression implies this, both ways they imply this expression. The purpose of this transformation is we want to convert these expressions in a simple or a minimal form. Okay, and this minimization may be in terms of some cost criteria, maybe the number of variables that are used, maybe the number of terms that are in the sum of product or product of sum. Okay, so usually there is some kind of minimization. The motivation is that if you can minimize either the number of terms or the number of variables, you need lesser number of gates to implement the corresponding circuit. Okay, so this is an important process that is done in any logic design process. So I mean, just give a simple example. So suppose I have a function of 3 variables x, y, and z, f, and let's say the function is described by this expression. One of the expression for this function is this. We can see that we can convert it to an equivalent expression, which is smaller than this, in the sense that it has less number of variables per term. It's smaller than this, so naturally we require less number of gates to do this. All right. So there are 2 important notions regarding to this. One is thing called a canonical form. Canonical form is if you take a set of expressions which are equivalent, then they will have. So if we consider this as an equivalence class or a partition or whatever, they will have a particular representation of the expression which is unique. That means if you take a particular canonical, the set of all equivalence expressions, representation will be identical. So it's like, I mean, it will be identical. They will, if you reduce it to the canonical form, if they are equivalent, they will reduce to the same canonical form. Okay, so this is one notion. Now there may be several canonical form. One thing you have seen is the sum of products form. This expression f of x, y, z is a sum of products form. Similarly, you can have a product of sum form. You can have x plus y plus z times x prime plus y prime plus z prime. You can have sum of product term. And just to quickly recapitulate, each of these x or x prime or y prime, z or z prime, they would be called literals. So this is a variable or they'll be called a literal. Okay, so you have a notion of a canonical form. There may be several, sum of product of sum. There are other also. There is a polynomial canonical form. So you express things like x plus xy plus yz plus xyz. It's called the Reed-Muller or the algebraic canonical. So there are other type of canonical forms also, but it's good to have a canonical form, but because it gives you a standard form and all your manipulations or your implementations can be sort of uniformized so that you can handle the standard form. Okay, so that's why you get to a canonical representation. There is another notion, the notion of minimality or irredundance. Note that these two are slightly different. It's not that canonical means irredundant or irredundant in general means canonical, but often they are the same. Okay, so what is a irredundant? Irredundant expression means that if you drop any one of the literal or the term in your representation, in your expression, then it no longer remains an equivalent expression. It no longer remains an equivalent expression. Okay. Say for example, in this expression for this function, say for example, if you drop xz, so or let me take this. So from this first expression to the second expression, you see you have dropped y, you have dropped x prime in the second term, you have dropped so some of the terms you have dropped. So even dropping some of the term do not change the logical value of the expression. It remains an equivalent expression. That means if that is so, then that term or that literal redundant, and this expression would not be an irredundant expression. Yes, if it happens so that even if you drop any one of the literal or term in the expression, it no longer remains the same expression, the equivalent expression, then we call it an irredundant expression. You cannot drop anything from it. You cannot drop anything from it. If you drop anything from it, it gets modified. So then we call it an irredundant expression. Note that a irredundant expression need not be a minimal. There may be multiple irredundant expressions which are equivalent. There may be multiple. For example, this is one example. You can have another expression which is again irredundant. You cannot drop anything from, but it's still equivalent. So you can have, for a set of equivalent relations, you can have multiple irredundant expressions. Each of them are irredundant in the sense that you cannot drop anything from it, but they are not unique. They are different. All of them are good. Okay, and also a irredundant expression, if you measure minimality in terms of the number of terms or number of literal, irredundant, but that does not imply it is minimal. Okay, it does not imply. If it is minimal, of course it is irredundant. You cannot drop anything from it. But being just irredundant does not mean, for example, maybe some of the terms I can reduce it into a smaller form. I cannot drop it directly, but I can transform it to another expression which is smaller, which is again irredundant, but it's minimal. So minimal is a slightly different concept. It means either the number of literals or the number of terms, they are the least possible. So these three concepts are important: canonical, irredundant, and minimal. All right. So what will okay. So now the next target for us is that we have studied all the Boolean algebra transformation rules and all such things. We would like to, given an expression, and this expression you may have in a different way. Maybe you thought of the, say we saw in the example in the first class, we thought of it up some way, we came up with the expression, somebody else thinks of it up in another way, comes up with an expression. So there may be different expressions, we can come up with the same thing. The designer comes up with several alternate expressions. Now this will describe two algorithms or the methods will convert it into a kind of a minimal form, or rather an irredundant form. Okay, so we'll actually study two canonical forms. First, we'll study the sum of product form. So our goal is, given an expression, we would like to convert it into a sum of product form, and we want this sum of product form to be irredundant and if possible minimal. That's our goal. We want sum of product. Why sum of product? Because there is a standard circuit implementation of sum of product. You have AND gates followed by OR gates in the second level, cascaded by an OR gate in the. So that's why you have sum of product. We'll also see, actually, we'll see the product of some form also. We will see that we can have an equivalent, redundant, and the minimal representation of the product of some form also. Okay, so let's say, all right. So one more important thing is that if you, for example, write in the sum of products form, we have a notion of an min term. As a min term, as you know, is a product term involving literals, either complemented or not complemented. Involving literals, it is a product of the variables, product of the literals rather. They would be called a min term. For example, this is a min term, this is a min term, and so on. Okay, so if we have, for example, I'll just use a notation to help you. Is that let's say I have a min term x prime y z prime. So I can as if represent a min term like this, because x will be true when x is 0, y will be 2 and y is 1, z prime will be true and z is 0. So this min term, I can write it this way. So as if I can list down the min terms like this. So I have x prime, y, z prime, 0, 1, 0. I have x prime, y prime, z. I can write it as 0, 0, 1. I can write x, y prime, z prime as 1, 0, 0. So for a 3 variable, I can kind of have a 3-bit representation of these min terms. If a 4 variable, I'll have a 4-bit representation. Okay. So sometimes for ease understanding, these min terms are indexed by the integer value of their binary representation. They are indexed by the integer value of the. So this would be the index number for x prime, y, z prime would be 2. The index number for this would be 1. The index number for this would be 4. So you can kind of number the min terms. Number the attach an integer to the min terms. Okay. So these min terms are there. There is one more. So the notion of min term is now you have already know very well. I'm just repeating it. The notion of min term is there. There is one more thing which is called a true min term. True min term. What is a true min term? True min term means, so if you have all these min terms, so how many possible min terms are there? Yeah, if there are n variables, there are 2 to the power n min terms, possible, or because each of the variable can be either complemented or not complemented. So if there are n variables, 2 to the power n different min terms are possible. Note one thing, these are nothing, but you can also visualize them if you write down the truth. If you write down the truth table x, y, and z, each of these 2 to the power, there are exactly 2 to the power n entries in the truth table for n variable, n number of variables, and each of the min terms, if we have a representation like this, correspond to one row of the truth table. Each of the min terms should correspond to one row of the min term. So 0, 1, 0 is a row, 0, 0, 1 is a row, 1, 0, 0 is a row, and so on. Right. So now, if you write the function will be 1 for some of the rows and 0 for the rest of the rows. So the rows for which if you pick up the corresponding min term, say for example it is the function evaluates to 1 for x prime y z prime, x prime y prime z prime, and so on. If it evaluates to 1 for each of these for each of these rows, then those min terms would be called the true min term of this function. The true min terms of this function would be called the true min terms of this function. Okay, so one simple sum of product representation of a function is that you just pick up your true min terms and add them by sum. Add them by sum. So that's what we have done in this function. We have picked up the true min terms. And then we have just added something, and that would give you a function. So this is a simple way. So if you want to express as a function is a sum of product from, you first write down the truth table. Each row of the truth table would be corresponding to a min term. Pick up the true min terms, the rows which are 1 of the function, and sum them. So that will give your sum of product representation. All right. So what we'll now do next is that, so given this kind of sum of product representation as a sum of all the true min terms, we'll try to simplify or reduce it. Simplify or reduce it by having a kind of a two-dimensional representation of the truth table. Representing modified form with rather a two-dimensional grid-like form, which is the Karnaugh map. Okay, and how does this Karnaugh map help us? Because you know this rule that if you have two variables capital A, or rather if you have any expression capital A and a variable A, that expression whatever times A, this will be a product. This may be, for example, xy. A is xy, let's say. So xy A plus xy A prime is xy. Okay. So this is the standard rule of Boolean algebra. You have already studied. You just take the associativity, and then A plus A prime is 1, and then you get this. Okay, so this algebraic rule can be very easily applied if you represent the truth table as a Karnaugh map. Okay, so now let's see how we write down the Karnaugh map. Okay, just one quick question: how many of you are already familiar with Karnaugh map? Anybody of you already familiar with Karnaugh map? Okay. Is there anything anybody is saying? Okay. Don't know at all. Anybody? Am I audible?
Yes, sir, you're audible.
Yes,
Okay,
sir.
okay, very good. Yeah. See, I got to told it. Okay. So this is what we repeatedly apply. So let's say how. So as I said, the Karnaugh map is a two-dimensional grid-like representation. Every cell of this grid would correspond to a min term of the variables. And so let's see. So this is a three-variable Karnaugh map. So okay. This is a 3 variable map, and so there will be 8 cells, to the power 3, 8 cells. Every cell corresponds to a min term. So this cell, the first cell, so what I do is I write it like this. The rows would represent different values of z, columns different values of the variable here x1. So the first row would correspond to z equal 1, 0, second row z equal 1, and this corresponds 0, 0 for xy, 0, 1. Note one thing, I am not writing it in the binary order. I'm not writing it in the order. This is important. 0, 0, 0, 1, 1, 0, 1, 1. That order I'm not writing. Rather, I'm writing it in a gray code order. I'm writing 0, 0, 0, 1, 1, 1, 1, 0. I'm writing it in the gray code order. The reason for this is that what I want okay, first of all, now let's see how does each cell correspond to a main term. So the first cell will correspond to the main term x prime, y prime, z prime, because this is 0, 0, 0. The second cell here would correspond to x prime, y, z prime, because this is 0, 1, 0. It's 0, 1, 0. 0, 1 for xy and 0 for z. So that is so what I have written here is that if you remember the previous indexing of the main terms in terms of their equivalent decimal value of the equivalent binary representation, then this would be this index numbers. So this, you see, these are the I have marked down the index number of the main terms in the corresponding cells in the Karnaugh map. Okay. So note one thing, that if you look at two adjacent cells in the Karnaugh map in any direction, if you look at two adjacent cells, they differ in terms of just one literal. If you look at the first term 0 and the 2 term, you see they differ only in the y literal, in the y variable. Y variable is complemented in the first and not complemented in the second. Similarly, if you look at 2 and 3, they differ only in the z variable. So two corresponding or two adjacent cells should differ only in terms of one single variable. Not only that, there is a, so that's what gray code, that's why you are using the gray code. Not only that, you can kind of, there is a cyclicity here. There is a this just a minute. Yes, good. So you see, if you look at this main term and this main term, there is also just a 1 bit difference. The difference is only in the x bit. Similarly, if you look at this min term and this min term, there is only difference in 1 bit. The difference is only in the bit x bit. Okay, and not only so, these two can, all these 0 and 4 and 1 and 5 can be considered as adjacent. So this and this can also be considered as adjacent. This and this can also be considered as adjacent, right? And kind of this and this can also be considered as adjacent. This and this can also be considered as adjacent. So all these are adjacent. They just differ by 1 bit each. Okay, one term each. Okay. So this is the Karnaugh map. So what I now do is that I draw my Karnaugh map and mark the true terms. You know, every cell of this Karnaugh map would correspond to a min term. Mark true min terms only. Mark the true min terms only. So this, let's in some function, this is the true min term. So function is basically x prime y z prime x y z prime plus plus so this function. So I mark the two min terms. So this I can easily do. I can look at the truth table, or if it is an already product term, I can look up them and I can mark the true min terms. Okay, so sometimes there is no rules for this. If you are given a Karnaugh map with corresponding true min terms attached, you can write it as a sum from. Basically means this is 2, this is 6, and this is 7. So 2, 6, and 7 are the true min terms, and the function is a product from sum of these 3 min terms. So this is written. You can equivalently have a product of sum from. So product of sum from would actually be the opposite. So if I write out, so in the rest, the product from equivalent from would be 0 and 1 and 3 and 4 and 5. So this basically means that this is x prime plus y prime plus z prime times this is x prime plus y prime plus z and so on. This is the sum of products. So these two are equivalent actually. So in the product from, you pick up the zero terms, the sum from of the true min terms, not the false min terms. Okay, so let us stick to this sum of product initially. Sum of product initially. All right, so I can extend this representation to more than 3 variables also. I can extend it to 4 variables. Say here 4 variables. So naturally 16 elements will be there to the power 4 because there are so many min terms. Let's say this is I write yz and wx. Y, wx are the variables. Wx I write along the columns and yz I write along the rows. Again, I write it in gray code form, both the columns and the rows. And this will be my x of the min terms corresponding to cell. And this is I have marked the true min terms. Let's say these are the true min terms. So the sum from this would be sigma 4, 5, 8, 12, 13, 14, 15. This will be the representation. In fact, I can extend it beyond 4 variables. I can make a 5 variable Karnaugh map also. So what will happen is that so 5 you know there will be 32. So this 4 by 4 block will repeat like this. Repeat like the same way. Same way it will repeat. Okay. Can actually make 6 variable Karnaugh maps also. So this entire structure will repeat downwards also. But again, the numbering has, so this, if you have a 6 variable, this will be kind of WX or ABC, D, like that. So it will be a larger Karnaugh map. Okay. So the thing is that see this will let us see that we'll use this 2-dimensional representation for our minimization purpose by finding some patterns in the location of the true min terms, the 1 min terms, by finding some pattern. We'll see that up to 4 variables, finding these patterns is easy. The rules are simple. But beyond that, say 5 variable or 6 variable, theoretically they are possible, but finding patterns in such large kind of becomes more and more complex. And beyond it's useless. There is no point in applying Karnaugh to minimize a 6 variable function. It's almost useless, or rather a 7 variable function. 5 and 6 are theoretically possible, but rarely adopted. There are better methods. Up to 4, it's very nice. It's very convenient. Okay. All right. So where are we? So now, given a function either as a truth table or as a sum of product from, we'll draw the corresponding Karnaugh map. We'll pick up the true min terms. We'll mark them as 1. Rest of the cells will stay empty. Only the true min terms will be marked 1. Now our next job is so we finally get this picture. Our next job is using this picture and some rules. We'll try to find an equivalent smaller expression function. called the simplification. All right. So what we want to do is we want to find out so-called cubes which enclose these true minterms. Okay, or which set of covers these true minterms. We'll find out cubes which will cover this true minterms. Okay, so what are the rules of forming the cube? First of all, so this is the cube. In the sense of this, you don't think that I am giving the name. This cube can be. This is also a cube. This is also what I call a cube. This is also what I call a cube. It's just you can think of it as a block also. We call it as a cube. So what are the rules for cube? Rules for cube formation. First of all, cube size has to be of 2 to the power m form. It can be 2, 4, 8, 16. It has to be of this. You cannot have a 6-sized cube. You cannot have a 7-sized cube. The cube has to be of this size. So basically what it means that this is a valid cube because it has 2 elements. This is a valid cube because it has 4 elements. This is a valid cube because it has 4 elements. But this is not a valid cube. This is not a valid cube because it has 3 elements. Okay, so the cube has to be power of 2s. Secondly, all the minterms, all the true minterms, has to be covered by at least 1 cube. It may be covered by more than 1 cube, but at least 1 cube has to cover it. Otherwise, it is not a valid cubing, not a valid cover. Okay, so in this example, you see that all the cubes are covered. So, anyway, so you see all the cubes are all the true minterms are covered by at least 1 cell. Some of the minterms are covered by more than 1 cubes, but that is fine. Okay, these two are the rules. And now we have a goal. Our goal of forming the cube is that the cubes has to be as large as possible. You want to form as large a cube as large sized cube as possible. As many true minterms you try to cover by a single cube. The cube should be as big as possible. Okay, now we'll soon see that moment you can form these cubes. Moment you can form this. So if you have a cube which is of size 2 to the power m, if you have a cube which is of size 2 to the power m, then the reduced literal will have m literals removed from it. It will be of the size, if n is the original number of variables, it will be reduced to a size n minus m. M literals will be removed or eliminated. Let's see why this can happen. Say so. Any of you, so you see, I have minterms have written. They actually, how many are there? 1, 2, 3, 4, 5, 6, 7. Are 7 written here? Let's write down. Let's write down. What are the 7? Anyway, I'm not writing down. Maybe that's 2. But let's take this example. So okay, so these are the 7. Yeah, it's already there. These are the 7 minterms. Now let's see. Now let's take this cube. let's take this cube. So what is this cube? This cube is, what is the first one? It is 1100, this term. What is the second one? It is 1000. Okay, so you see, you eliminate the variable which is changing in among these two cubes. So these two are changing, these two are changing. You eliminate that, and this you keep. So these two minterms will be reduced to this expression. What is this? This is W, because W X Y Z. Let me write this. This is W. W is 1. X is X prime, because this is 0 here. Z is Z prime. Okay. And what are the original thing? Original thing, what was this? This was W X Y prime Z prime. I'm just looking at these two. I'm not looking at the others. And this was, what was this? This was W X prime Y prime Z prime. Okay. So this is the expression corresponding to this. Looking at this, I have reduced it to this. So this X variable I have eliminated. Okay. And since this is a cube of size 2, M is 1, so I have eliminated one variable. Let's look at another example. Let's look at this one. Let's look at this one. Okay, so what are the minterms? If I write down W, X, Y, and Z, what are the what are the true minterms? So this is Wx is 1, 1. Actually, Wx is 1, 1 in all of them. And YZ is 0, 0 for the first, 0, 1, 1, 1, 1, 0. Okay, so this is this thing. Anyway, this is this thing, this one. So you see, this one is completely varying. This one is completely varying. Varying in the sense that Y all that there, and these two are constant. So I will reduce it to, what is this? Only Wx. So if you write down this minterm plus this minterm plus this minterm plus this minterm, because they are covered by this cube, they can be reduced to this. And since this is of size 4 to the power 2, two variables are eliminated. So the rule is, what you want to do, you see, you find a cover, you find a cube to cover, look at the minterms inside the cube, see which are the variables which are both uncomplemented as well as complemented form. In the cube, which are in uncomplemented as well as complemented form. Eliminate them. And the variables which are either only in uncomplemented form or only in complemented form throughout the cube, those you keep, those you don't eliminate. So here you see W and X, they are only in uncomplemented form, or they are 1, 1 throughout the. So we will not eliminate them. Whereas Y and Z, they are both in complemented and uncomplemented form. They are both in uncomplemented and uncomplemented form. So I can remove these two. I can eliminate these two. Now let us look at this box, square box. Can anybody tell what are the variables I can keep here and what are the ones I can eliminate? Anybody? Please speak up.
Here W is changing, so W can be removed.
W can be removed.
And Z is also changing, so Z can be removed.
Okay. So I have, what is the equivalent product? What is the reduced product corresponding to this square box? Tell me the expression.
XY dash.
The X into X prime.
XY dash, XY bar. So that's the expression corresponding to this. So if we look at this total Karnaugh map, this will be XY bar plus, this is for this square, YWX for this vertical kind of thing, and this one, what is this one? WX prime Z prime plus WX bar z bar. So this is the reduced expression. Whereas you see the original expression has how many min terms? 1, 2, 3, 4, 5, 6, 7. 7 min terms I have reduced to 3 products. 3 product terms. Right. So this is how it happens. Let's take another example. So this is a simple example. And that's what I have done. Let's take the okay. Let's yes. All right. You see here are the min terms. So naturally, so what are the cubes that will be formed? This is one cube. Okay. One thing, by the way, note that there is not a single way, there is not a unique way by which I can form these cubes. I can form cubes in different way. For example, I can form a cube like this also. I can form a cube like this also. Okay. I can form, okay, but first before that, so there is no unique way. Before that, you see, as I said before, there is a wraparound. So this and this are, oh, by the way, one thing I forgot here, I think one thing I forgot here. Oh no, I have erased them. Okay, so the cells that form a cube, the cube has to be of size 2 to the power m. It has to cover all the min terms, and the cells within a cube have to be adjacent. I think that was obvious. They have to be adjacent. Otherwise, you cannot include them in a cube. They have to be adjacent. Similarly, here they are adjacent. Otherwise, you cannot form it. You can only enclose adjacent true min terms. Okay. But as I said before, this is kind of a wraparound. So this and these are adjacent. So I can form a 2-element cube as if by merging these two. I can form a 2-element cube. Okay, so that's a valid cube. Okay, so as I told you that this is not unique. So I could have actually made something like this. I could have made one thing like this, and maybe one like this, and maybe one like this, and maybe one like this. That was also possible. Okay, so this is an alternate Karnaugh map for this, and that will give you a separate different expression. But actually, what you want to do is that I'll tell you the rules for that. So the rules for forming the cubes are okay. It has to include adjacent true min terms. It has to include any true min term has to be covered by at least one cube, and the cubes can be of size 2 to the power m form. And after you form the cube, you examine a cube, you find out what are the variables that are not changing, and what are the variables is in complement as well as uncomplement form. You eliminate them, others you keep, you get the reduced expression corresponding to that cube. This way you do for every cube, you sum them. You get a reduced sum of product form for the original sum of product form. Okay, so as I showed you that there are multiple Karnaugh maps you can form using a set of min terms for a single function, but we would like to have the minimal one. Now, minimal one in the sense that which gives you the smallest expression after elimination. Okay, so here is the rule. Cover all the true min terms of the one cells with the smallest number of cubes. So you should try to minimize the total number of cubes that you are using. Okay, and if you have two possibilities where you are covering all the cells and your total number of cubes are also the same, you should try to use that each cube is as large as possible. Okay, so a cube, so one thing naturally that comes in that if one cube is a proper subset of another cube, another larger cube, you should keep only the larger cube. This directly follows from that. Okay, and if there is more than one way of covering the map with a minimal number of cubes, the smallest number of cubes, select the cover with the larger cubes. Okay. Also, a cube contained in any combination of other cubes already selected in the cover. A cube contained in any combination of other cubes already selected in the cover is redundant because they are all by the consensus. You will see that. So here is my rule of, I'll come back to this, what is the consensus theorem. So here is the rule of minimization. First cover those cells that cannot be combined with other cells. So they have single adjacent cell. Next combine this one cells that, so first try to form two-sized cubes. Then try to combine them to form four-sized cubes. Okay, so this way. And so your minimal, so I have not given you an algorithm for doing this, that because often there is no algorithm, this just by visualization. The rule is that you should try to cover all the cubes. You should try to minimize these three rules. You should try to minimize the total number of, and if you have multiple minimal covers in terms of the number of cubes, you should take the one where the cubes are larger. Okay, so cubes are as large as possible and as few as possible. Of course, with the condition that every one cell is covered by at least one cube. Here is an example. So, by the way, can you give an example of an Karnaugh map which cannot be minimized? Can any of you give an example of the Karnaugh map which cannot be minimized? Let's take a 4-variable Karnaugh map. Can you tell me what will be the true mean term so that it cannot be minimized by this process? Okay, you think on it. Let me quickly tell this. So this is an example what I was saying, that okay, you have this 4 cube, which is as large as possible, but this once has to be taken care also. So you also need these 4 two-sized smaller cubes. You also need this. Okay, all right. So can you give an, so what about this Karnaugh map? Can it be minimized? Any of you? Can I minimize this Karnaugh map? Can I minimize this Karnaugh map?
No, sir.
No, sir.
No, sir.
Okay. So this is a typical checkerboard structure. This is actually W XOR X, XOR Y, XOR Z. You cannot minimize this. Okay. I don't know. All right. So, so I think this is clear. You should practice some examples in the sense that, okay, I think you got the idea that how do you form these cubes and how do you get a reduced expression from the cubes. You have to practice some. It's not very difficult. In fact, the possible number of patterns is only 2 to the power 2 to the power n. So you should practice some. There are typical cases. 3-4 things you have to take into mind. First thing is that you should try to form large cubes. Second thing is that these wraparounds are. In fact, one more thing I want to forgot to mention. In fact, this and this and this and this, they form a 4-sized cube. Okay, so basically you can not only wrap it this way, you can also wrap it this way. So you kind of, I don't know if I can draw it, you get a kind of a torus-like structure. I don't know. Okay, you get a torus-like structure, toroidal structure. And if you look at the toroidal structure, then these 4 corners will be kind of something here. Okay, this part will be down, wrapped down. So this will be this kind of structure. So you can minimize if these 4 were my min terms, true min terms, then I can form a 2 by 2 sized, 4 sized cube out of it. What will be the reduced expression for this 4? What will be the reduced expression? Anybody? Just tell me the reduced expression. Anybody?
X bar.
Tell me the reduced value. X bar, Z bar. Okay, so these are basically two rules. They are not much complicated. These are basically rules, but okay, I mean, if you have a small function with only 4 variables, these are very nice rules. But as you can see that these are only 4 variable functions, so this will always not suffice. But in the early days, this was a very popular method. Maybe not today. In the next class, what we'll see is that you can do a dual of all these Karnaugh map minimization for a product of sum form. So what we do in the dual, here I am looking at only the positive min terms, the true min terms. I will look at the false min terms in the dual form. And then, in fact, I made a mistake when I wrote the min term. Anyway, they have to be complemented. Okay, so you can do a dual of this. You can actually instead of a sum of a product, you can write a product of sum by looking at kind of the dual Karnaugh map, where I look at the false terms rather than the true min terms. Okay, but we'll do it in Monday. Thank you. Let me stop here. So